Good morning and welcome to the morning session of the last day of the winter school. Today we have Benny Pinkas, who's going to talk about private set intersection. Benny is the director of the Cyber Research Center at Bar-Ilan University, Israel. He received his PhD from Weizmann Institute in 2000, and he has worked in the research lab of Intertrust Technologies, HP, Google, and VMware. His main research areas are cryptography, computer science, and privacy, with a focus on secure computation. We're very happy to have Benny here. Benny, the stage is yours.
Thank you, Kamit, and I'm very happy to be talking at the school. I'll be talking about private set intersection. I'm going to have 2 hours. In this first hour, I'm going to show a quick introduction to PSI, private set intersection. Then I'm going to talk about the basic PSI protocol, which is based on Diffie Hellman, but also about its relation to oblivious pseudo-random function evaluation, ORPF. And I'm also going to talk slightly about the technology behind the CSAM detection system that Apple rolled out this summer and then discontinued. Okay, so let's go to the talk. So I'll be talking about introduction to PSI, Diffie Hellman-based PSI, and PSI from ORPF, and the Apple CSAM detection system. So what is PSI? So we can think about the following functionality. We have 2 parties, Alice and Bob. Each one of them have a set of inputs. Alice has x1 to xn. Bob has y1 to yn, and Bob should learn the intersection of the 2 sets and nothing else. And we could also think about a protocol where Alice also learns the output. And we can also think about computing functions of the intersection, some simple functions like the size of the intersection, or whether the intersection is greater than some threshold, or more complex functions. And we can also think about a multi-party version where there are more than 2 parties, and we want to compute the intersection of all of the sets. So PSI has surprisingly many applications. So it can be used for information sharing between different parties, say that have threat information, strange things that happened on their network, and they want to compare them. They can be used. It can be used for checking matching between different parties. If you look at databases and join operation, then they're basically PSI, computing the intersection. Also, when you do analytics, many times what you want to compute is the condition probability of some feature A given some feature B. And when you compute the conditional probability, you need to compute the probability of the intersection of the 2 things happening. There are also applications for identifying mutual contacts between users and all the context of a new user of the Signal app and all current users of Signal, or for computing ad conversion rates, and I'll describe this example in more detail. So for analytics, we can think about an example, say, where university knows the IDs of workers and students, and the government know which persons were vaccinated, and you want to compute the percentage of people that were vaccinated inside the university, okay? So you don't want to reveal this information to each other, just to compute this percentage. So for this, you need to know how many people are in the intersection. Another interesting example is this story from the New York Times, where apparently there are people who go to many fertility clinics and serve as sperm donors in many of them because they want to have many children. And then the fertility clinics want to identify, if the certain, person came to more than one clinic, but otherwise they want to keep the identities of sperm donors private. And this is another example from very interesting Israeli startup, where the cases where you have a merchant, say Alice, that has a new customer, and you have a network of merchants and banks, and each one of them has lists of a few million customers. And when the merchant comes, she wants to know what the other merchants in the network know about the customer. Is it a good guy, a bad guy, what they know about it? And she wants to do this while hiding the identity of this customer, and they want to hide the identity of their customers. But together, they want to learn something about new customers. So in general, Alice, the merchant, has a new customer. Each other member has a set of customers and some rating. And Alice wants to learn the rating of the new customer according to the other members. Okay, and they should not learn who's the new customer. And you can do other things like, say, if Alice receives a purchase from a certain credit card to a certain address, she wants to know if the other merchants had also purchases by the same credit card to this address, say, a few days ago, and there was no dispute, so maybe that's okay. And what's interesting to note here is that here Alice's set contains only a single item. So here we compare one item to many items. So in addition to computing the intersection itself, we might want to do analytics on it. So here we have the sets, but Bob doesn't want to learn the intersection, but he needs to learn some function of the intersection. Okay, say the size of the intersection. And another option is with payloads. So here, each item has a payload associated with it, say the rating, and you want to compute some function of the items in intersection and the payloads. So here it's a more complicated, more complex function. And as an example, there's a, these days very known application of Google that use PSI for ad conversion rate. Ad conversion measurements. And so what happens is that, say, a credit card knows who came to a certain merchant and made purchases. And Google they know which users saw a certain ad, say, for that merchant. So basically, what you want to learn is how many purchases were made by people who saw this ad. So here you don't want to compute the intersection, you want to compute the sum of the transactions made by people that, say, saw the ad yesterday and came to purchase something today. And this purchase can be in an offline place, say in an ice cream stand. Okay? And of course, what they do is probably more complicated, but this is the basic thing that they want to do here. So some computation on data associated with the items in the intersection. Okay. So why did I investigate PSI? So it's relevant for many applications, but this, it took us time to identify this. But also, this is a function that cannot be efficiently solved by generic MPC. So generic MPC works by computing over a circuit, which computes the function. And if you want to build a circuit that computes the intersection, basically you have to compare n items of Alice to n items of Bob. So the simplest way to do that we'll have to do n-squared comparisons, and that's too many. I mean, if say n is a million, so the circuit will be too large. So here is a case where you need to design a specific solution for a problem for which the generic MPC is not efficient enough. And also a nice property is that the solutions turned out to be quite interesting. So that was a nice extra when we worked on this. So one approach to design PSI protocols is using oblivious pseudorandom functions. So a pseudorandom function, you can think of something like AES. And here, if I don't know the key and I just get to see the output, it looks random to me. It's pseudorandom. So a PRF is keyed with a function K, and someone who does not know the key, the output seems for that person to be pseudo-random. Even if that person knows the input or even chooses them, the output is still indistinguishable from random. So this is a pseudo-random function. And a protocol for oblivious pseudo-random function evaluation, or OPRF, is a protocol for securely computing a PRF. So Alice provides an input X, Bob provides a key K, and then Alice learns FK of X, say the encryption of X with AES, with the key K, or another pseudo-random function. Another version, which seems strange at first, is that Alice provides a key K, an input X, and then the functionality chooses a key K, gives it to Bob, and gives to Alice FK of X. So Bob does not choose K here, just he's given K by the functionality. After he's given K, he can compute F on any function that he wants, okay? But he doesn't choose K. So this seems odd, but apparently it's important where it's useful where it's not important for Bob to choose the key. It's only important for him to have a key which Alice doesn't know. And in PSI, this is the case. So in PSI, we're mostly going to use this version because it's more efficient. Okay, so here's an example of a specific pseudorandom function based on DDH. So this is the DDH assumption. I hope that most of you know it. So in a DDH group, giving a generator G and random A, B, and C, you cannot distinguish between these two tuples. So this is a tuple G to the A, G to the power of B, and G to the power of AB. And this is just, random 3 elements in the group. And here the values should be in the right range, etc. So this is, very basic assumption in cryptography. And here's the PRF based on it. So let's G be a group in which the DDH assumption holds. Let H be a publicly known random function mapping into G, and we model it as a random oracle. And K is the key. And the function is very simple. Given an input X, we hash it using H into the group, and we raise to the power of the secret exponent K, the secret key K. And the claim is this is a pseudo-random function. Okay. Now, typically we implement this in elliptic curve groups, using elliptic curve cryptography. But for me, it's easier to describe this in this notation. Okay, like computing modulo P. But most implementations are in elliptic curve groups. So here's a protocol for securely computing this pseudo-random function. So Alice will learn f of x with Bob's key without learning the key. So Alice chooses a random value r, and she sends to Bob h of x to the power of r. Bob raises this to the power of his secret key k, sends the result to Alice, and Alice takes the truth of what she received, and she computes h of x to the power of k. Okay, so she received the output of the pseudo-random function. So why does this look to be secure? So the only thing that Bob sees is a value in the group raised to a random exponent. So this is uniformly distributed, so Bob doesn't learn anything. And what Alice sees is basically 2 values. This is random. This is that value raised to the power of k. But actually, given her input and output, her input is x, and her output is the output of pseudo-random function, h of x to the power of k. So she can compute these 2 values that she sees. So she compute them by taking x, computing h of x to the power of r that she knows, and taking the output of the function, raising it also to the power of r. So Alice giving her input and output from the protocol, which she should learn, can simulate her entire view. So this also seems to show that she is secure, and you can easily prove security based on that. So actually, this ORPF is now quite widely used. There's even an internet draft defining it. And you can also think of variations where this is a verifiable ORPF. Basically, the server can prove that in all invocation, it uses the same key. So basically, the server publishes G to the K, and whenever it runs the protocol, it proves to Alice that whatever she sent to him, he raised to the same power K. And this is today quite widely used. So how can we use it for PSI? So I'll describe here a very known PSI protocol, the most basic one, designed by Catherine Meadows in 86, I think, and then redesigned afterwards over and over by other people. And I'll describe it as using an ORPF. So Alice has, of course, the initial descriptions were not describing it as an ORPF, but this is how we're going to describe it. So Alice has this set of values, and Bob has this set of values. She chooses the random alpha, and Bob would choose a random key beta for the ORPF. Alice sends to Bob each of her values raised to the power of alpha. And usually we use elliptic curve groups to do this. Bob takes each of his inputs, computes age, and raises to the power of beta. So basically, he sends the output of the PRF on his inputs. And then he takes all of the values received from Alice, raises to the power of his key beta, and sends to Alice. Now, Alice takes these values, takes the alpha root, okay? So basically, she gets her input, applying age to them, and then just raised to the power of beta. And then she compares the values she received from Bob to the values that she computed. And if one of the xi's is equal to one of the y's, then she see equality. So this is the entire protocol. First, what's nice about it, it's very simple. Okay, if you think about it for a few more minutes, you completely understand it, and it's also very simple to implement. This is extremely important. Now, and we describe it as an ORPF. Okay. Now, why is it secure? So before describing this protocol, I should have asked you to design a PSI protocol, and most people come with the following insecure version of PSI. So the insecure version is for Alice to take her inputs, send to Bob some hash function of the inputs, SHA of her inputs, and Bob will compute, SHA of his inputs and compare them. So this initially seems secure for non-cryptographers because this function is one way. So given the output, you cannot reverse the function. But if Alice's inputs come from a small domain, say it's a phone number, then Bob can run a dictionary attack over all possible phone numbers, compute SHA over all these numbers, and compare them to the values he received from Alice. So the problem, the attack against this, trivial but insecure PSI protocol is that Bob can compute the function himself about over the entire domain of possible inputs for Alice. What's nice in the ORPF protocol I showed you earlier is that what Bob sees here is a function of Alice's input, but this function depends on the alphas that only Alice has. And what Alice sees is a function of Bob inputs, but this depends on beta that only Bob has. So they cannot do this dictionary attack. Okay. So this is basically what I said. So you can also prove this by simulation. Bob can simulate his view in the protocol because basically what he sees here is pseudorandom. This is exactly the output of the pseudorandom function with a key that only Alice has. And basically what Alice sees here, these are pseudorandom values, and these are values which either are equal to for items which are not in the intersection, the pseudorandom, and for items which are in the intersection, basically one of the values that Bob sent raised to the key that Alice has. So Alice can simulate this. This takes some more time to prove, but she can simulate her view. Any questions so far?
Yes, so there is one question.
Okay.
So the question is, can PSI be considered as a special case of PIR when only one party gets the output?
Okay, that's a good question. They both talk about two servers and learning something, while hiding what you want to learn. It's also several differences. So first in PIR, there's only one item, not many items. And mostly in PSI, the main difficulty is that you compare many items to many items because you don't want to do the n-square comparisons. Another issue is that in PIR, at least in the basic definition, you care about hiding the query from the server, but you don't care about the client learning more than one output. More than one. So in PIR, you care about preserving the client privacy. So the server should not learn what the client is querying about, but you don't care about the server privacy. You care about, so in theory, the client can learn about more than a single item, more than about the intersection. Also in PIR, the focus is about the communication being sublinear, and in PSI, it can be linear communication. But sometimes we combine PIR in PSI solutions. Okay. So let me continue. So what we showed you is basically this protocol is a template for running PSI, okay, using OPRF. So basically what you do, you run an OPRF version where Alice gets the output of the OPRF on all of her inputs. And Bob sends to Alice the output of the PRF on Bob's inputs, and then she can compare them. So this is basically what we did with a specific PRF, but we can do it with other pseudorandom functions. Now, thinking about it, Bob doesn't have to send to Alice the PRF output of his inputs, because she's just going to compare them to what she computed. So instead, he can send to her shorter outputs, just long enough so that she can compare them to what she computed and have a very small false positive probability. Okay, so you can have hash this output to be much smaller according to what false positive probability you're willing to tolerate. And apparently, you don't have to send the list of outputs. What Bob should send is a data structure called the dictionary, which enables Alice to take what she learned in the OPRF protocol and check if it's in this list. And by sending a dictionary, you can even compress the message from Bob even further. So where is this important? It's important when you do PSI of sets of unequal size. So Bob sends to Alice a dictionary encoding of the PRF outputs on his inputs. And then for each input of Alice, they will run an OPRF in which she'll learn this output and check if it's in the dictionary. Now, if Bob's input is much larger than Alice's, then he can compress all these values to be as short as possible based on whatever false probability that we allow. And then for each item of Alice, they'll just do a computation which has like a constant overhead. And also, Bob can send these values to Alice even before she learns her input, and then she can check for a match whenever she has an input. So gradually, whenever she has an item, she can compare it to Bob's values. So this is very useful where her input size is much smaller than Bob's. Now, there are many implementations of OPRF, and basically what we want to use is the one that gives us the best performance for PSI. And I won't describe them. I only describe the basic one based on Diffie, Hellman, and random walk. And for some applications, we need verifiable OPRF or security against malicious, and sometimes we use OPRF for other applications, but we're talking about PSI. So this was the first half of my talk. Any questions?
No questions.
Okay. So in the other half of this hour, I will be talking about a very recent PSI protocol that received a lot of attention. And this was a system deployed by Apple, or announced by Apple for detecting CSAM, which is child pornography, or it's called child sexual abuse material. So this is my interpretation of it, both based on how I read the documents that Apple published. Okay. And what's important about this case is that it received a lot of publicity and a lot of debate about, social, legal issues of this solution. People talked less about the technical issues, and I want to focus here only about the technical issues. We can devote an entire hour just to discussing the high-level social issues, but I'm not going to discuss them here. And what's nice about these issues is that, this quote from Mariana Pfefferkorn from Stanford, where she says, about this system, that may your research area be relevant to current affairs is may you live in interesting times, curse disguised as a blessing for the academic set. So this is, a saying which is, known in many languages as it's a blessing, but living in interesting times might also be a curse. And when your research is relevant to, the world, it seems like a blessing, but it's also a curse because it makes things much more complicated than working in complete theory. And in this case, it was, a huge, headache. So just some background. So CSAM is child sexual abuse material, which is terrible material, and it's against a law and against any norm to be using or viewing these images. But apparently the internet is overrun with such images. And this is from the New York Times. Last year, tech companies identified more than 45 million online photos, okay? Which is harrowing, I mean. Okay. Now, the question is what you do about it. So all companies, including Apple, when they received a court order, okay, they provide what the court asked from them, or some requirement for law enforcement, okay? But this is when they have a requirement, at least in the United States or Western countries, if you have a court order or requirement, a lawful requirement for law agencies to get to a specific item, okay? So they tell you, give us the data of this person. And this depends on the law in different countries, okay? This is not about scanning all your data or all the data of all users all the time and looking for these horrible pictures, okay? Still, you want to be searching for this data, okay? So what happened in previous years, it was reported that Facebook 20 million such photos on these. And the companies, when they find and Apple only found 250 such photos last year, okay? So, of course, it's, case that, Apple, it's the case that Apple was not searching for these photos because they didn't want to search photos unless they get a court order, okay? Also, what we're going to discuss here is not about searching for photos in phones or in messaging apps. It's only about photos which are uploaded to cloud storage, okay? So what do other cloud companies do, okay? There's an organization in the United States called NCMEC, or National Center for Missing and Endangered Children. It's the only organization outside of law enforcement which can view these photos. It computes a hash of these photos, some hash which is supposed to be resilient to small changes like cropping and changing the size, etc. So it computes this hash using a known hash algorithm, which they try to keep private, but it's not secret. They send the hash list to cloud companies like Facebook or Google. And then when you store your photos on Facebook or Google, they go to each photo, they compute the hash of that photo and compare it to this hash list. And when they see a match, they report it to law enforcement because they must report it, okay? So this is possible because your photos are stored in the clear, okay? And they can scan them, and they're not required by law to do it, but they do that. And Apple didn't want to scan your photos, okay? Now, just to make it clear, they are only looking here for matches with known content of photos that, as far as I know, were declared by a court to be CSAM, okay? I think they even know the names of the children in each of these photos, okay? They're not analyzing your photo and see if you have a nude, photo of your children, etc. They're looking for specific known photos, okay? So anyone holding these photos is definitely operating against the law, and the companies are reporting them. And Apple did not do that, okay? So the system that Apple wanted to design, okay, was required to have the following properties. Apple always say Alice instead of Apple, but it's Apple, of course. Apple doesn't learn anything about images that do not match the known CSAM list. So they don't want to look at your other images, other photos. Apple doesn't want to access the photos of a specific person until they identify, say, at least 30, that's an arbitrary threshold that can be changed, matches from that specific user. So if you have like 1, 2, 29 photos by accident, that's okay. There's a certain threshold. If you have more than that, only then they'll be able to open your photos and check them. The risk of incriminating, innocent people to be extremely low. And also, once they identify that someone has at least 30 such images, then the photos will be opened, or some low resolution version of them, and someone will manually look at them, and only if they see something suspicious, they will report this. So this is to protect users against Apple watching the photos or reporting an innocent user. They also want to have the following requirements. Users cannot access or view the database of CSAM images or even the hashes, because then they'll be able to check if a certain image is in this database. And users cannot identify which images of them were flagged by the system as CSAM. So basically, the only output that the user sees from the system is if that user had more than 30 images, then maybe the police will knock on that user's door. Any other output the user doesn't see. Okay, this is to protect, I would say, society from users who try to use the system to identify, what images are in this CSAM data. So this is an ideal view of how we'd like to, use MPC to implement this. So NCMEC provides a hash list to Apple. Apple provides it to a trusted, an ideal world to a trusted party. The device provides hashes of uploaded photos. If the number of matches is smaller than 30, nothing is done. If it's more than 30, then Apple gets the identities of the matches. So this is what we want the trusted party to do. And it seems like a PSI protocol. You compute, say, the intersection. And the device will compute the hashes, compute the intersection. I mean, there are some requirements which are dependent on the application, okay? And any solution might solve them. And the ideal functionality, it's a bit, hard to define in it these requirements. So first is that, okay, we want Apple to provide the same hash list to all users, so they cannot check in my iPhone for certain set of photos and saying other people look for other set of photos, say in other countries. And this is to protect, say, governments from asking Apple to look for, say, political photos or something like that. And also, this should be the photo received from NCMEC. Okay, the list received from NCMEC. So you can do this using actually zero knowledge proofs. You can prove this. It's not very hard to do it, but I won't discuss it here. Also, what happens is that the user doesn't, we don't compare all the photos of a user at the end of the year. We want to compare them one by one as the user uploads them. And this should be a non-interactive protocol. So he uploads the photo and then he doesn't interact more with the server. And also, once you get this list, they want humans to look at the photos before reporting people, just to be on the safe side. So basically, this entire system is just to, filter suspicious users from, all, billions of users. And then the suspicious users will be inspected by humans. Okay, so how does the system work? NCMEC sends Alice Apple the hash list. Apple encodes the hash list as Diffie Hellman tuples, and I'll describe it in details, in a Puku table, and sends this encoded hash table to the device as part of the operating system. The device, when you upload a photo, you compute a hash of it. You compute a key based on that photo and this hash table. You use that key to encrypt a low-resolution version of the photo, and you send it to Apple. And then the PSI magic, if there are at least 30 matches, then Apple will be able to decrypt the low-resolution versions, inspect them manually, and report. So this is how the system operates. And some things to notice. First, Apple only gets the hash list. They don't see the photos. Actually, it's against the law for them to see the photos. Okay, and look, in different countries, they might be different agencies. Okay, so what's considered CSAM in one country might not be CSAM in another country. So that's a big issue for them. Then they encode the hash list. So what the user receives, the device receives, it doesn't receive the hash list, but some encrypted version of it. Okay? So the device doesn't see the hashes. Now the update is received as part of the operating system. This ensures that all users all the world receive the same hash list. Okay, so they cannot target me specifically because I receive the same operating system update as others, and also updates, happen every few months. The list cannot change too often. Now, this hash is only computed for uploaded photos as part of the upload mechanism. So it's not about photos on my machine, only about uploaded photos. However, most users upload all of the photos to iCloud, but they can choose not to. And then you compute a key. With the key, you encrypt. And if there are more than 30, at least 30, but not less, then you can Apple decrypts and inspects manually. So this is like some things that they had to focus in the design. And I think that here, it's a good time to ask if there are any questions so far.
No questions so far.
Okay. So what we see here is that the device doesn't learn the hash list. The device doesn't learn if there's a match because it doesn't get any output in this protocol. And Apple do not learn anything about non-match photos because only if there are more than 30 matches, they can decrypt. So how do you do this? So here we get to the PSI part, which is also based on Diffie Hellman. Also, everything is in elliptic curve groups, but I use exponentiations. So the server, when it prepares this hash table that will be sent to all users, it picks a random secret key, exponent A, which will be global for the entire world, okay? And then they construct a cuckoo hash table, but you don't have to know what cuckoo hash is, hash table, storing the hash list. So for every photo hash X that they received from NECMEC, they store the value, okay, say X is mapped to the group, and they store the value X to the A in the table in location T age of X. So this is a function which maps to a location in the group, location in the table, okay? This is not the hash function that was used by NECMEC to hash the image to a value. And then what you use, the hash of the function, you raise it to the power of A and you store it here. Okay, so actually this is a cuckoo table where each item can be stored in 2 locations. Okay, but just to simplify things, say that it's stored in just 1 location. And also, if there are collisions and some items we cannot store, we just drop them. And in some locations, the table remain empty. You just put them random entries. Now, basically, what you compute here is X to the A in a Diffie-Hellman group where A is secret. And since X is already the output of a hash function, this is the pseudorandom function we discussed. So basically, what Apple stores is a pseudorandom values. What Apple puts in empty entries is random values. So the whole table looks completely pseudorandom to users. They don't learn anything. So what the users, the client, get as part of the operating system is this table and G to the A. So this all looks completely pseudorandom to them. Something else to note is that if you send a table which is not large enough and you have too many collisions, then you cannot put all items here. Okay, so in terms of collisions, they say just drop some of the items until you can fit all items in the table. Okay. Now, usually when we talk about PSI, we don't want to do this. We have the inputs. We want to compute the intersection of the input sets of Alice and Bob. We don't want to drop any item, and we work a lot to make sure that we don't drop any item. Here, basically, they want to compare photos to a list of maybe 200,000 CSAM images. If, say, 10% of these images, they have to drop from the table, okay? And this is a random subset. So basically, for the bad users, 10% of, the, bad images will not be identified. But if someone is bad, then, there's also very good probability that its photos will match the 90% of the CSAM database, which they don't drop. So here they don't care about dropping some of the photos. Okay. So what's important for security is what's called Diffie-Hellman self-reduction of now and Reingold. Okay, so look, this is a Diffie-Hellman tuple. G to the A, G to the B, and G to the AB. Suppose we take random values C and D, and we compute G to the D, this is D, and times T to the C. And we also take this value, G to the L, L to the D times P to the C. So basically, we take a random Diffie-Hellman tuple, take the first and third items, raise them to the power of D and C. This is the first value. Takes the second and fourth item, raise them to the same powers. This is the second value. Now, what you see, the red items are the blue ones raised to the power of A. So basically, if this is a different Hellman tuple, then S is Q to the power of A. Okay? S is Q to the power of A. If this is not a different Hellman tuple, then you can show that these two values are uniformly random. So S is completely independent of Q. Okay? There's no relation between them. Okay, so the important thing here is that if we start from Diffie-Hellman tuple, we get that S is Q to the power of A, and whoever knows A, Apple, can compute S given Q. Otherwise, S is completely random. This is what they're going to use. Okay, so what happens on the client side? This is the most important thing. The client has a photo. Okay, so it computes the hash of the photo, this photo DNA hash. It has the ID of the photo. And it also has some associated data, which is a low resolution version of the photo. Okay. It picks random C and D, and it computes Q, which is hash of photo X to the power of C, G to the power of D. In S is what you have in the table that you received from Apple for the location of that photo, raised to the power of C. And G to the A that you also received from Apple raised to the power of D. Now, if this photo happened to be in the database sent by Apple, then what you have in the table here would be X to the power of A. This is how we constructed the table. In that case, it would be X to the power of AC, G to the power of AD. Basically, we started from a Diffie-Hellman tuple, and what we get is that S is Q to the power of A, because here you get XAC, GAD, so S is Q to the power of A. Otherwise, if S, what you have in the table in this location, is not X to the power of A, then this is completely random, using based on the random self-reduction of Diffie-Hellman. So the idea is the client computes these two values, okay? He's going to send Q to the server as part of the upload, and then use this S as a key. Now, if the item that client uploads is a Diffie-Hellman tuple, then then S is Q to the power of A. The server knows A, and the server can compute this key. Otherwise, the key is completely random. So basically, the nice thing here is that the client computes a key that for items which do not match the system database is completely random. And for items which do match the system database, the server can compute that key easily. Okay, so just stopping here. The client sees a table, but this is completely pseudo-random. If the client doesn't know the key A that only Apple knows. And for items which are not in the table, the client encrypts, I didn't say what it encrypts, but the client encrypts something with a key which is completely random. Okay. Any questions?
Yes, there are several questions.
Okay.
So going back to the protocol description as in before the technicalities. So there's one question on, yes, here. Do you know how big the encoded hash table is? Because it could be rather large because there could be a lot of reported images.
Yeah, so we just said what's in the encoded hash table for each item. We store one or two values in an elliptic curve group. So say we store 32 or 64. No, we store 250 bits or 500 bits per item. Okay, so if you have say 100,000, 200,000 items here, it's going to be megabytes, but it's part of the operating system. It's the operating system update. It's fine.
Okay, so one more. Why does the cuckoo filter need to be part of the OS?
Okay, so this is not something for the PSI protocol. It's something for the general picture. So and a possible attack would be that the government wants Apple to track me, and they tell them, give Benny a specific, hash table that looks for political images or for, something which is specific for me. Okay, so by putting it as part of the operating system, and the operating system is universal, all people all over the world get the same operating system. You can ensure that everyone gets the same, list of hashes. Okay, so you cannot do different things in different, to different people or different countries. Also, the operating system is updated not very often, every few months. So, and this, for database also is not uploaded very often. So this is to ensure that, governments cannot track people, specific people or change what they track for very quickly.
All right. Another question. For the cuckoo table, can you specify the hash function in such a way that all the hashes can find a place in the table? Because you want to compare image hashes against all the hashes in the CSAM list.
Okay. So this is the cuckoo table. And okay, those who are familiar with that know that the size of the cuckoo table should be like 2 plus epsilon times the input size. And when you look at the documentation that the Apple put, it's like 1 plus epsilon times the input size. Now, this seems like a typo, okay, or maybe epsilon is 1 point something, but it's not a typo. So actually, they had a cuckoo table which is quite small, okay? And this is to improve on performance because this basically cuts the size of this thing by a factor of 2, okay? So by having a smaller cuckoo table, okay, you inevitably you're going to have a lot of misses. So something like, I just invented a number, 10% of the items, but you can run a simulation, okay? We will not find a place for them. But for this specific application, it's not bad because you just, instead of looking for a huge database of CSAM photos, you're looking for something which is, 90% of that database. And it's not, a random subset of that size. So any bad guy is likely to have, many items for that 90% section, subset of the bad database. So the size is about 1 plus epsilon times n. I'm not sure what epsilon is.
Okay. Right. So another question, is the client honest? Otherwise, they can just always use a random key.
Okay, so the client is running the Apple operating system, and you assume that it follows the protocol, because otherwise yeah. Okay, so I want to continue, and then we'll ask at the end because I want to make sure that I can. Okay, so the important thing here is you want to do threshold PSI. If there are less than 30 matches, Apple should not learn anything. Okay, so it goes like this: the client picks a random master key. This is associated data key, AD key, for all items. For each item, it takes the data of that item, which is the low resolution version of the image, encrypts it with this master key. Then it generates a Shamir share of this master key with a threshold of 30. It encrypts these two values, where S is the key that Apple can only learn if the item is in the CSAM database. And with this key, it does an authenticated encryption of the pair of the encryption of the photo and the share. So if there's no match, Alice learns nothing. Otherwise, Apple Apple learns a share and encryption with the key. Okay, so it learns a share and encryption of the key with the key. After 30 such shares, it can recover the key and learn everything. Otherwise, it cannot recover this. So this is good, but the problem here is that if this is authenticated encryption, Apple learns whenever it sees a share. So then they can see, and the government can ask them, tell me for which persons you got 29 shares. So we cannot decrypt anything, but we know that these are not, saints because we had 29 matches for them. Okay, and Apple want to hide this. So they want, if they'll have less than 30, they don't want to learn anything. So they want to somehow hide who has 29 matches, who has 28 matches, etc. Okay, so you want to hide the number of matches. So what happens is that the devices, the phones, will also send at random dummy matches. So messages that the servers will be able to decrypt, and they'll get something that looks like a share and like an encryption, but this is a dummy share. So what the server will end up with is some real shares and some dummy shares, and it must be able to decrypt whenever the number of real shares is more than 30, at least 30. So basically what we get here is a kind of an error correction problem. Okay? And the problem is that the server doesn't know before it gets 30 real shares, which are the real shares, which are the dummy shares. And the solution is based on a decoding algorithm of Corpus Smith and Sudan. And basically what you have is like enhanced Shamir shares. And if you want to be able to decrypt, identify given state T, which is 30 correct shares, and S dummy shares, you use the system. The caveat is that the size of each share is now increased to be, by a factor of S plus 1. So each share is not one item in the field, it's like S plus 1 times an item in the field, which is much larger. So if, say, T is 30 and the number of dummy elements is at most 100, some random distribution, then each share will contain 101 field elements, which is, for me, it looked, very bad. But actually, they said it's not that bad because, each share is much larger. But in the context here, you upload a share together with a photo. So the photo is like, 2 megabytes. And then here you're going to upload, 100, items in a elliptic curve group. That's nothing compared to the image. So this is important for PSI. Like, you should think of the context. Here we don't care about increasing the communication of PSI because the other parts of the system is much less efficient. So the associated data, what we encrypt is a low resolution visual derivative of the image. If you have 30 matches, then you can decrypt this because you get the share, and then human operators can check these low resolution versions. If they look like CSAM, they report the user. Okay. Now, there are many potential problems which I didn't discuss here. And these were like the big problems, okay? First, they might be false positives. So they set the parameters so that happens with very low probability. They can be attacks like on the machine learning, trying to attack the photo DNA algorithm. I think that there are good solutions for that, but in this context, but I won't go into them. Another issue is that people didn't like the fact that Apple is scanning things on our devices. And this is, I can understand this. But, there's a problem. I don't want to go into this, but there are 3 things which are all good. One is we don't want people to be using CSAM because it's obviously bad. The second thing is that we want our storage to be end-to-end encrypted. So we don't want servers like Apple or Google or Facebook be able to see our photos. This is also something that we want. And another thing is that we don't want them to run any scanning on our devices. Okay, you cannot have all these three things together. If you want to scan for CSAM, you have to either do it in the cloud or some component together with the device. So here is an attempt to find, some trade-off between the two, the different requirements. The public didn't like this trade-off. Okay. Okay. Another issue is, who controls which items are searched for, governments, etc. So Apple tried to somehow control this by having like a single list for the entire world, and they said that they're only going to put in the list items which they receive from at least 2 governments. But that's also a question. And the main thing that people didn't like is that it's a first crack in the dam. So far, companies did not search on our devices for the purpose of law enforcement. This is the first place where this is happening. It's only happening as part of the upload process for items that we upload, but the public didn't like this. Okay, so these are relevant papers. So the story is that Apple suggested this. There was a huge outcry, and then a few months later, they somehow rolled back. They didn't, these things disappeared from Apple's website, and they don't, talk anymore about the system. These links still work. So if you want to recover the technical descriptions that Apple put, you can recover these documents. This is the description that I put, which is a bit more technical than the talk I gave here. And that's about it. And this is the case of PSI with specific requirements about how you do it. You do it image by image, etc. You need to do threshold solution, which I haven't seen before. You have a solution which is also based on random self-reducibility, and which I also haven't seen before. It's it's a very nice system. The whole picture is very complicated. So, any more questions?
Okay, several questions, but we'll just pick a few.
I can also, I'll answer on the Slack afterwards.
Right. So one is, can you use something like Bloom filters to avoid dropping of hashes? This is with regard to the cuckoo hashing.
Yeah.
And
so,
yeah.
Okay. So yeah. So basically, you want to use the base system you have, the best encoding you have. You can use. I think that the best solution is cuckoo hashing with 3 where you look at 3 locations. I think that they could have potentially improved a little the storage that they use. But the important thing here is that just observing for this specific application, they don't care about dropping part of the server's input, because they don't care about dropping part of the database of bad items. That's that's the most important thing for me there. But also in general, usually Bloom filters are less efficient than cuckoo hashing. I don't recall a single example where Bloom filters were better. So I think that from a technical perspective, cuckoo hashing are, at least my experience is that it's better. Yeah.
Okay, so another one is, why upload dummy shares instead of just uploading nothing when the number of matches is below 30?
Okay, so the issue is, Apple, whenever I don't, but whenever someone sees some images, they can decrypt and they see that they get a share. Now, suppose they see that someone had 29 shares. They cannot decrypt what that person uploaded, but we know that this is probably not a good guy. So the government can come to them and tell them, whoever, for which you can decrypt more than 25 shares, we want to talk with that guy. Okay? And Apple don't want this to happen. So what happens, all phones, even, phones of complete saints, okay, which is like 99.99% of the population, will upload dummy shares. A random number of them according to some distribution. So I upload 80 shares, you upload 75, someone else uploads 90, and before, among these 90 shares, 30 are true shares, they won't be able to decrypt. So it will be hard for them to distinguish between phones of random innocent people and phones of people who had 29 shares. Now, it's not really that simple, because my phone is going to upload a certain number of dummy shares, and the phone of a bad guy is going to upload something according to the same distribution plus 29. So his phone will upload more shares than mine, but still we have some doubt, which hopefully will be enough. Yeah. One more thing I want to say about this, it would have been nice for them to prove something about differential privacy that they provide there, but they didn't prove anything. So I suspect that it's very hard to prove it, because otherwise they would have done it. But I don't know any information. Yeah.
Okay, we'll take just one last question. Would an homomorphic encryption based solution that runs on a remote server be better accepted than an on-device scanning system?
Yeah, so I think what's important here, so that would have been nice. I mean, I'm maybe not very efficient. So if I get it right, it's like a proxy. When I upload things, they go through a proxy and they are scanned over there. And I'm assured that they don't scan anything on my phone, just when I upload it. And Apple cannot see the images. That would have been maybe a better solution, probably not efficient. Right now, they only implement this as part of the upload process, but I have trust them to do that. So that would have been good, but it might not be very efficient.
Well, there are a bunch of questions more, but then I guess we should stop here.
So I'll go to the Slack channel after the second lecture.
Okay, thank you very much, Benny. We will resume after the break for the second talk about private sector section.
Great.